Okay, in the previous lesson, we looked at determining critical numbers. So maximums and minimums. So these are our extremum. Just let me fix the screen here. So sometimes these critical numbers are maximum and minimum values, but sometimes they're not. So for example, let's say we had the function f of x is negative x to the power 3 plus 1. So if we want to determine the critical numbers, we find the derivative f prime. So let's find the derivative, negative 3x squared, and we set it equal to 0, and we solve for x. So x would be 0. And we could find the y coordinate by just subbing back into the original equation, and we find f of 0 is 1. So we have a critical number when x is 0 at 0, 1. But if we look at the graph of negative x cubed plus 1, which is here, we can see here's the point that we just found the critical number. We found the critical number to be 0, 1. We can see that it is not a maximum or a minimum. In fact, the graph continues, it's decreasing, and then it continues to decrease. So 0, 1 is not a maximum or a minimum. So although it is a critical number, it is not always an extrema. So if you think about, so the first derivative or the derivative is the slope of the tangent. So if we think about a function that has a maximum, and we drew a tangent line on the left, and then we drew one on the right, we can see that here we have a positive slope, and here we have a negative slope. So the sign of the slope of the tangent changes. Right, it goes from positive to negative. If we had a graph that looked like this, the slope of the tangent on this side would be a negative value. The slope of the tangent on this side would be a positive value. So again, when we have a minimum value, the sign changes. But we can also have graphs like the one we just did, where maybe we have a graph that looks like this. And we determine a critical number, but on here, the slope of the tangent is positive, and on this side of the critical number, the slope of the tangent continues to be positive. So sometimes at a critical number, the sign does not change, and it is not a maximum or a minimum. This is actually called a point of inflection, and we'll look at that later. But for now, our purposes are, can we determine a maximum or minimum based on the sign of the slope of the tangent, or what is often called the first derivative. So this leads us to the first derivative test. So it is a test that is used to determine whether a critical number is an extremum or not. If the derivative, the first derivative, changes from a positive to a negative, then it will be a local minimum. So that's what we just looked at here. So this one is from a negative to a positive. So if the slope of the tangent changes from a negative to a positive, it will be a local minimum. If it changes from a positive to a negative, it will be a local maximum. And if it does not change, it is not a local maximum or minimum. And so this first derivative test allows us to determine whether critical numbers are maximum or minimum values or not. So the first thing, here we have a function. The first thing we're going to do is find the derivative. So we get 3x squared minus 6x. We'll set it equal to 0 so that we can find those critical numbers. So we'll do that by factoring. We have a common factor of 3x. And so we have critical numbers at x equals 0 and x equals 2. So we will make an interval table to check these intervals. So I'm going to check between negative infinity and 0, between 0 and 2, and from 2 to positive infinity. And we'll put our factors down the sides. And then we're going to look and see what the sign is on that slope of that tangent or that derivative. And then that will tell us whether the function is increasing or decreasing. So we'll pick a number less than 0, so I'll pick -1. And that will give me a positive result for the slope of the tangent, which means the original function was increasing in that interval. And I'll pick a number between 0 and 2. I'll pick 1. And I get negative, so that means that the function is decreasing. And then I'll pick a number bigger than 2. And the function is increasing. So what I'm looking for is a change in sign. So here I see that the function is increasing and then decreasing. So that makes that a local max. And then here at x equals 2, the function was decreasing and then it's increasing, which makes it a local min. So we can then conclude that we have sign changes at x equals 0 and x equals 2. So we have a local maximum at x equals 0, and we have a local minimum at x equals 2. So that is our first derivative test. We are looking for a sign change to determine whether it is a extremum or not. Okay, let's look at another example. So here we have a different function, 3x to the power 4 minus 4x to the power 3 plus 2. So we'll start out by finding the derivative, which would be 12x3 minus 12x2. We will set equal to 0. We will factor. I see a common 12 and an x squared. And therefore we have critical numbers at x equals 0 and x equals 1. So we'll make an interval table to check these intervals. So we'll check between negative infinity and 0. We'll check between 0 and 1. And we'll check between 1 and positive infinity. Put our factors down the side. And then we're checking the derivative, so the sign of the derivative, which will then tell us whether the original function is increasing or decreasing. So we'll pick a negative number. It's squared, so that's going to be positive. And a negative, so a negative, so it will be decreasing. Pick a number between 0 and 1. I'll pick 0.5, so that's positive, negative, negative, decreasing. And then I'll pick a number bigger than 1, increasing. So we can see that at 0, although 0 is a critical number, the sign does not change. It is decreasing up to 0, and it continues to decrease at 0, between 0 and 1. So that is not a local max or min. I see a sign change at x equals 1. So this would be a local min at x equals 1. So although we have two critical numbers, we have a local minimum only at one of them. So you have a local minimum at x equals 1. Local maximums, we don't have any. We have none. So at x equals 0, we are going to have a point of inflection, which we will look at in the next part of the guide, where we look at points of inflection and concavity. But the first derivative test allows us to determine what our critical numbers are and whether those critical numbers are in fact local maximum or local minimum.